Hello everyone. So today we're going to talk about a Wheatstone Bridge and how it functions. But before we do that, here's a funny picture of a hippo working on a Wheatstone Bridge. Well, thank you everyone for dropping by to go over the Wheatstone Bridge. So just to give you a little bit of background on the Wheatstone Bridge. So the Wheatstone Bridge was invented by Samuel Hunter Christie in 1833. And so this thing's been around a long time. And then so Charles Wheatstone came along and he popularized it and refined it in 1843. So it's been around for about 183 years, if you can believe that. That's amazing. So the Wheatstone Bridge looks something like this. We have a power source here, VS. And then a lot of times what you'll do is you'll see it drawn like this. It'll be a diamond shape, which I don't quite understand why it was always in a diamond shape, but it looks pretty cool. Usually I'll redraw it, and I'll show you here in a second what I do with that. But so you have four resistors, four parallel resistors, and if you're not familiar with that, just I have a video on solving parallel circuits, and you can see kind of how a parallel network works. But it's really a simple design, and that's what's so elegant about it. So R1 would be here, R2, R3, and we can call this R4 or RX. And the whole purpose of the Wheatstone Bridge is to measure an unknown resistor like RX. So as long as you know, as long as you know these two resistors here, or these two. It depends on the ratio of the resistors, but as long as you know some of the resistors, you can easily calculate Rx or measure it. But the way I usually do it when I'm working with it, because sometimes it can be drawn sideways. Some people draw it on its side and everything, but the way I like to draw it is and this is just how my mind works, I like to see it more like a parallel network because I understand that a lot better than I do. But here would be the resistor. So really this is all it is. It looks, just like this. And then we have R1, R2, R3, and RX. And so current's going to go this way. You're going to have IT. And as we've talked about before, here's still IT, but it splits. It goes off, like I1 goes this way, and then I2 goes this way. So the currents literally split off, and then they come back and reconstitute back to IT again. And that's due to the KCL, the Kirchhoff current law, which just means these branch currents have to add up to IT. So IT is equal to I1 plus I2. Okay, and then the voltage is always the same, like across these nodes. So the voltage here and here and here will be VS. So this is all VS right here. So that makes it easier to visualize that. But it's good for measuring unknown resistance and low values of resistance. All right, so let's look at it with some values associated with it. So let's go ahead and draw the circuit again this time. This time we're going to add 5 volts. And we're going to draw the bridge here again. I'm going to draw it how I normally draw it, just a parallel network. Also, using different colors is helpful too sometimes. Like if you have a colored pencil, you can draw these branches at different colors and things to kind of help you understand which branch you're on and all of that. It's smudged. Pardon me. I smudged it here a little bit. So we know this is 5 volts, right? And we know this is R1, this is R2. This is R3. This is R4, right? So this is 10 ohms. We're going to add that in. 20 ohms. And I just picked these values out of the air just to make make it easier to understand because we're going to be dealing with a ratio, what I mentioned for ratios. So these resistors, if you notice, are the same ratio because this is a 1 to 2 ratio, which is what we're looking for, because since the voltage is the same, then if the ratios are the same, then these measurements right here will be balanced. So what we're going to do is we're going to have a meter right here, and we're going to be measuring the voltage, or you could measure current, it doesn't really matter. And when the voltage is 0 volts, measured 0, in other words, when there's no difference in potential here, when it's 0, when A and B, we'll call this A, and this node right here B, when these are the same voltages, there's no potential. And if there's no potential difference, then current can't flow. So in other words, if this was 3 volts or 3.33 volts or whatever it's going to be right here, then and this is the same, then no current can flow. You have to have a difference in voltage for current to flow. Or let's say, for example, and this is just an example, but let's say this was 3.33 volts, and this was 3.33 volts, then the potential difference is 0. If it was like maybe 3 volts and this was 1 volt, then you'd have a 2 volt difference, and then current could flow. So that's the power of the Wheatstone Bridge. As long as it's balanced, then this will always read 0. And we'll explain why it being balanced is a good thing. But just remember, this is just a ratio. So this is like, 1 to 2. And you can see this 50 goes into 51, and then 50 one time, and then it goes into 100 two times. So, and then 10 goes into 10 one time, and it goes into 22 times. So it's still a 1 to 2 ratio here. So so always remember that. And really that's why at a glance, if you know the resistances, you can just look at these ratios, and then you'll know. Oh, I know it's balanced. You may not know the actual values, but you'll know it's balanced just by the ratio, and that's how. We'll come up with a little equation that comes from that. So just remember that we have Ohm's law. We're working with always. V is equal to I times R. And of course now these are directly proportional. So since the current is not changing, in these, we know, for example, the current's going to be the same here in this node, like through each of these resistors, right? And each of these resistors are going to experience the same current in this node. So V is equal to I times R. So when resistance goes up, the voltage goes up. When resistance goes down, the voltage goes down. So just kind of remember that. So since the circuit's a 1 to 2 ratio, and we got that from this right here. Right here. So in other words, it was, R1 was equal to that, R2 was equal to that, right? And then so that equal to 1 over 2. So R3 is equal to 50, and R4 is equal to 100, right? So then we know that, these can cancel out, and it's 5 over 10, that's 1 over 2, right? And that cancels out. So that way we know this bridge is going to be balanced. And if it was anything different, then we would definitely know it wasn't balanced. So we know that, so now we can actually come up with an equation for this. So, and we really don't even have to have current involved, since we know it's just a ratio, and we know that voltage is the same. We don't even have to worry about calculating current or anything. So that might be a relief to some people, because then, we could actually take the 5 volts and, divide it by the, 30 ohms here and come up with the current, and then multiply the current times each one of these, or just really by this one, and then we could come up with the value that way. But there's an easier way to do it. So we know that R1 and R2 is just a ratio. So what we can do is say that R1 over R1 plus R2 times Vs is going to equal to the voltage across this node, right? Voltage across this resistors, in other words. So in other words, we're just taking it's a percentage. It's all about percentages. So the percentage of voltage dropped across R1 is going to be equal to this guy. So that would equal to 10 ohms over R1 plus R2, that's 10 ohms plus 20 ohms is equal to 10 ohms over 30 ohms. And that's going to equal to 1 over 3 times Vs. And that's going to be equal to 1/3 times 5 volts. And then that's going to equal to roughly 1.67 volts. Okay? So you have that. And then now if I wanted to calculate R2, it's just R2 over, oh, well, actually, I don't want to say R2, V1. So V1 would equal this. This is V1. This is V2. Okay, so if I want to calculate V2, then it's R2 over R1 plus R2 times Vs. That's not a 5, that's an S. All right, then it's going to be, R2 is going to be 20 ohms over 10 ohms plus 30, 20 ohms. I'm jumping ahead of myself. And so that'd be 20 over 30, all right, ohms. And that's, well, times Vs is going to equal to 2/3 times Vs, which is 5 volt, 5 volts is Vs, is equal to 3.33 volts. And if you multiply this times 2, really I had to round up here. Really it's 1.66, and then goes on for a long time. So really, if you think about it, if I multiply this times 2, so it's 14 carry my 1, that's 13 carry my 1, 3.34, which, I kind of rounded up here and I didn't round up here. So it's a 1-to-2 ratio is what I'm trying to say. So it's 1-to-2. So it kind of proves what we just said. That's why you don't really have to do the calculations too much. I mean, you can just, if the values are even, and that's the only problem, is if they're not even, then it might be a little trouble. But if you saw something like this and it was even, you'd know that, oh, okay, I know this bridge is balanced because it's a 1-to-2 ratio on both sides, and it's always going to be the same. So, and it's the same. It's the same thing for this up here as well. Like, so if I wanted to say V3, then I would say, V3 is going to be, R3 over R3 plus R4, right, times Vs, right? So that's going to equal to R3 is 50 over, well, 150, because that's, I don't want to jump too ahead of myself. So it's just going to be 50 plus 100. So it's going to be 50 over 150. All right. And then, of course, now we're kind of, well, times Vs is equal to, and of course, these cancel out, right? So you end up with 5 over 15 times Vs, which is equal to 1 over 3. Same thing as what we did up here. So times Vs is going to equal to, 1.67, which, times 5 is 1.67 volts. And same here for V4 will then be R4 over R3 plus R4 times Vs, which is going to equal to 100 over, 50 plus 100 is going to be, 100 over 150, which is equal to 10 over 15 times Vs, which, of course, 2 goes into 10. 5 goes into 10 2 times. 5 goes into that 3 times. Turns out to be 2/3, right? Times Vs is equal to 3.33 volts. Oop, that's a 2, but that's a 3 now. Okay. So just to kind of show you that, so now what we're having is, so VA then is equal to, so if I take a measure right here across R2, so what's V2? Well, it's 3.33 volts. So VA is equal to 3.33 volts. And then VB, if you measured here, VB is equal to the voltage across R4, right? So that's V4, that's equal to 3.33 volts. Oops, missed a 3. So that just means that, so now, we know that, so VA minus VB is equal to 0 volts. So this bridge is balanced. So yeah, very, very powerful indeed. I mean, so what's cool about this, and right now you're probably thinking, well, what does it matter, that it's balanced or not? Well, it does matter because if you have it balanced, we know exactly what all the resistances are, and as they change, we can measure the little changes in voltage, and you can actually electronically do something with that. So you could create a voltmeter out. I mean, I guess you could create a voltmeter, or you could create a thermometer, or you could measure the strain on a bridge or something, or whatever you wanted to measure. You could use a strain gauge in there. So yeah, very, very interesting to work with. So also we can use it to calculate an unknown resistance, and that's where I was kind of getting at on the strain gauge thing. So let's say we have a circuit, and this is going to be closer to what we'll have in the lab. We'll actually do one in the lab here in a minute, but we'll use smaller numbers, or more even numbers, and I'll explain why. So let's say this is 5 volts, and let's say this is, and I'm just kind of arbitrarily picking these numbers just to make it easier to calculate in your head. So hopefully, if you're ever having a test, hopefully they would give you some nice round numbers to work with. This would be, let's say we'll do 70 ohms here in R2. And then, yeah, it would be cruel to give you some uneven numbers to work with. Hopefully they'd have mercy on you, just give you some even ones. So let's say this is Rx. We don't know what it is. And here's R3. And this is what I was saying. Let's say this is a strain gauge. A strain gauge is just a neat little resistance thing where if you bend it or stretch it, it'll change the resistance of it. And then I don't really have one handy to show you, but I do remember a long time ago in college I worked on a project. I didn't get to follow all the way through, but we used a Wheatstone Bridge inside of a rocket, a model rocket, and we had a strain gauge in there to where a piece of metal would bend and it would change the resistance. So the strain gauge, as the rocket went up, and they wanted to measure the G-forces of it and everything by measuring the resistance. So we had a Wheatstone Bridge in there, and then when the strain gauge would bend, when it would lift off, or when it's coming down, it'd bend the opposite way, then you could measure the differences in voltage and then turn that into something useful. You could calibrate it and use it, turn it into something useful. So let's just call this 50 ohms. So yeah, we'll do this 50 ohms right here. Okay, so we have no clue what this is. And what's cool about this too is we can add a variable resistor. This is a variable resistor, this symbol right here. It just means that we can actually have it like a wiper blade inside the resistor. You can turn a knob, and this resistor will change resistance up to a certain level. So if I had a 10K ohm, and it's called a potentiometer, so if I had a 10K ohm potentiometer, it would go from 0K up to 10K. Yeah, but usually for this type of circuit, you don't want to have it where it just goes. I mean, you want to kind of have it where it's in here somewhere under 10K, so that you can really adjust it well. So, and then what we would do is, since we don't know we know the ratio is 1 to 7 here, right? So it's 10 into 7, that's 7. So it's 1 to 7. And we know this one's 50. We just don't know this one. So all we have to do is, remember how I said before, is when the ratios are balanced or the same, the Wheatstone Bridge is balanced. So what we would do is we would take this guy and, we would adjust it. In this case, I have 70 ohms, but we would adjust it. And let's say, we adjusted it to 70 ohms, and this happened to be 0 volts, then we would have the bridge balanced, and then we would know the resistance here, and we could calculate it. So in the lab, what we would do is you wouldn't really know what that is. What you'd do is you would have these two resistors here set up, and this potentiometer set up, and you would just adjust it until it balanced out. And then you would take the potentiometer out and measure it, and then you'd know, oh, in this case, let's say it was 70 ohms. Oh, it's 1 to 7. And then you'd know, oh, since it's 1 to 7, this one has to be 1 to 7. And then we just calculate it that way, and then we'd know what Rx is. So again, that's all we're doing is calculating the ratio. So let's say, so what I was saying before is, so let's say we did, adjust this potentiometer, and it said 10 over 7. Or 70, 10 over 70. Well, that's supposed to equal to 50 over, and this is R1, by the way. R1, this is R2, and this is, of course, this is R3 and RX. Well, then we know, okay, well, so, and really all I have to do is multiply that times 7. So 10 over 70 is equal to 50 over 350, because 1 over 7 is equal to 5 over 35, which is equal to 5 will go into 5, 1, and it'll go into that 7. So 1 7 is equal to 1 over 7. So that means it's balanced. So that's kind of, in real life, that's how you would do that. And because of this cool thing here, when a bridge is balanced, we don't even have to worry about the voltage or the current in this calculation. All we have to do is state that R1 over R2 is going to equal to R3 over RX, based upon what we just said here. If you have the same ratio, and the ratio, so we know the ratio is the same. Oh, I kind of messed up there. Is the same. So I make a lot of mistakes writing. So when a bridge is balanced, we know the resistance ratio is the same. So what that means is now all I have to do to solve for Rx, all I have to do is just use some algebra, and we would say Rx. So Rx would go over here, right? And then we'd flip this, and it would be R2 over R1 times R3, which is really equal to R2 times R3 over R1. And that's equal to, so in this case, for example, R2 was 70. R1 is 10. And then we're going to multiply that times R3, which is 50, which is equal to 350. Which is equal to, not 350, but 3,500. Oops. Oh, it's supposed to be this. Right? 3,500 over 10. You can get rid of a 1. So that's equal to 350 ohms. And that would be Rx. So that's pretty cool. So really the whole thing, all you got to remember is balance your bridge and just use this equation right here, and you can solve for Rx. I mean, how cool is that? Because, let's say you had a strain gauge up in a bridge somewhere, or maybe it's in a strain gauge in a location that you just can't access it. Well, as long as you had access to measuring the voltages and you had a little knob that you could turn and figure out what the resistance is to that, then you could definitely figure out what that was. So that's pretty cool. So let's move this aside, and we're going to calculate, or we're going to say what we're going to do in the lab. All right, so in the lab, and remember, the calculations that we did over there, on like over there, meaning right here, all these calculations are perfect mathematical models. I always try to say that, because in the lab, things are going to be different, because, you have, meters aren't perfect, resistors aren't perfect, you have some resistance in wires, and you have, and you have tolerances of resistors. No, like if I pick up a 100 ohm resistor, even if it's a 1% tolerance, it's going to vary a little bit. It can be off by 1%. So that's the fun thing about the lab, is it doesn't have to be, perfect, but you can kind of tell if you're way off. If you're really way off, then that's understandable. Then okay, I got a problem. But if you're close, then most of the time you're okay. So in my kit, all I had was, I don't really have a huge kit right now with all kinds of resistors and potentiometers and things. I have some things, but not a ton. I need to buy some things. So all I had right now was, I had a 4.7 k ohm, and so these numbers are totally weird. I really wanted like maybe a 3 k ohm or something. So all I had was a 4.7 k ohm resistor, and I had a 10 k ohm resistor, and then I had another 4.7 k ohm resistor and a 10 k ohm resistor. And then, of course, we're going in the lab, of course, we're going to have A and B. And we're going to have a DVM, a digital voltmeter, right here. We're going to be just measuring just like that. This is measuring just like that. So in this case, then, VA is going to equal to, VS. Oh, I guess I need to complete my circuit, don't I? Well, that's horrible looking. Oh well. So, so let me just kind of erase this. This is awful. Anyway, so you can see though. But so current is flowing this way, right? And we know current's flowing that way and this way, and then it's all going to combine again. This will be IT, of course. I always like to draw these so you kind of understand what's going on. And this we're just going to call it I1 and this I2. Like before, right? And then it comes out as IT, and then it goes back to the return, and just ignore this. Okay, so to get VA, here's VA and here's VB. All right, so to get VA and VB, so VA is going to be equal to, and I'll be posting these on buildcircuitswithrich.com. So buildcircuitswithrich.com, that I'll have all these calculations, and I always try to put my notes in there, even if they're messy. At least maybe you can remember, oh yeah, I remember him messing up right there. That was kind of funny. So VA is going to be equal to VS, and this is VS, by the way. So we'll just say 5 volts times, it's going to be R2, which is, so it's going to be R2, which is 10 k ohms, which is really 10,000 ohms, right? And then it's going to be R1 plus R2, which is going to be 14,700 ohms. So that's going to be our calculation there. And that's going to be equal to 3.4 volts. All right? And so, and the reason the reason that's this way, because so VA, if you just want to look at it mathematically, then VS times, R1 over R1 plus R2. All right? So that's the the general equation of what we're doing here. So then VB is going to equal 5 volts times, so VB is over here, right? It's going to be really the same thing, and that's why I chose these, because it'd be real easy to see. It's really the same calculation, right? It's 10,000. Try to make it easy on the lab, so that way you're not spending time trying to do math in your head. You can just kind of see it. And really, the ratio is about whatever this ratio is, whatever 4.7 to 10 and 4.7 to 10 is. You can tell these numbers are the same, so it's definitely going to be balanced, at least mathematically anyway. And of course, that'd be 3.40 volts. And the reason that is because VB is equal to VS times R2 this time, excuse me, R4 this time. Oh, I'm sorry, that was R2. I made a mistake. That was Vs times R2, R1 plus R2. So, because we're taking it across here. So this one's going to be R4 over R1 plus R2. My apologies. I'll see if I can edit that in the video and put a little note here. But anyway, so that's the ratio there. Whatever that is, I don't know really what that is, and I don't even have to know. I just know as long as these numbers are the same, you know, and this is, you know, in this case, just looking at them, you can tell. That's why I kind of picked those numbers. So just to double check, so VR1, which is that one, would be Vs times R1 over R1 plus R2, which is going to equal to 1.6 volts. And then, of course, you know, VR2 is going to equal to Vs times, well, I said R1, didn't I? And then Vs is going to be, VR2 is going to be Vs times R2 over R1 plus R2, right? And of course, that's going to be equal to the, you know, what we just came up with, right? And then VR3 is going to equal to Vs, and it's going to be times R3 over R3 plus R4, right? And that's going to be equal to 1.6 volts. And then VR4 is going to equal to Vs times R4 over R3 plus R4. That's going to be equal to 3.4 volts. So you can see everything's perfectly balanced. And so now what we're going to do is, in the lab, what we're going to do, so that's just kind of one measurement, one thing we can do. So the next thing we're going to try in the lab is we're going to take this circuit here. We're going to take, oops, I guess I better get up here where you can see it, 5 volts. And we're going to take this, and we're going to say, or we're going to leave the R1 at 4.7K ohms. And in the R2, we're going to put in a variable resistor, and it's going to be a 10K ohm potentiometer, which is what I, that's just all I had. And so, and I'm going to do a little bit of a trick here, because I only had a 10K ohm potentiometer to work with, and so we're going to use a thermistor in the lab, and we had to kind of do a little bit of a different thing. But anyway, so for these numbers up here, you know, we're going to use that. But so we're going to use a 10K ohm potentiometer, and then what we're going to do is we're going to have a and here in a second I'm going to hopefully not throw you off, because so this is R3. Now here's where it gets kind of weird. We have a thermistor, and it's going to be like it's going to be, I think at room temperature it was about 12K ohms, and our potentiometer only goes up to 10K ohms. So what I'm going to do is I'm going to add in another 4.7K ohm resistor here, and I know this looks really weird, but really just, I mean, this is where you have to kind of improvise in the lab. I was kind of measuring it ahead of time, and I thought, okay, this is going to be Rx. And we're not going to know what this resistance is, but I wanted to measure, I wanted to see what it was, so that when I put it in the circuit, it's not, you know, there's no surprises. And sure enough, it was 12K ohms, so it was bigger than my potentiometer. So what I had to do is I had to add in another resistor here, so that now I've got like 4.7K ohms plus 10K ohms, so that's 14.7K ohms, and the 10K part is variable, so I can go down to all the way down to 4.7K, or I can go all the way up to 4.7K. And luckily, this thermistor is a the resistance goes down the hotter it gets. So I had to kind of get where I could get up here around, to get it to balance out. Initially, I had to get up around 12K or whatever it was. So this way, that provides me enough resistance to do that. So that's why it kind of looks a little weird. But just pretend this is just one resistor that's 14.7 k ohms, and then then this guy will be, and it's an adjustable one. That's the maximum it can go for 14.7 k ohms, and we can adjust it and get it to balance out. It's just that I had too small of a potentiometer, and of course this is A and B, and I'll kind of show you that in the lab here in a minute. Okay, all right. So let's. I think it's time for us to go to the lab. So let's go to the lab. All right, so we're in the lab, and I've got my meter, and I've got a potentiometer, and this is what that looks like. You can measure the resistances off these little, like if I just measured, well, I'll just do it right now. So if I measure here to here, for example, and I've got this set to measure ohms. If I measure here to here, I'll measure 10 k ohms, approximately, right? Because we're in the lab, and well, maybe I can get a better grip on that. Okay, 10 k ohms, and it's steady. Now, if I wanted to take, make it variable, I could measure here and there, and see I can move this knob. I can't really do it with the. Well, actually, maybe I'll put some clips on here. Okay, so I got some clips. I didn't want to waste your time me fiddling around trying to get clips, but the way to do this is if I measure here and here, this is the ends of it. It's just like a big resistor at this point. And you can see I'm measuring 10 k ohms. But if I take it and measure it here, though, now what's cool about this little guy, see how it adjusts? See it moves? So I can go down, I can go up all the way up to 10, and I can always go all the way down to, 0. So I didn't think it would go all the way to perfectly 0. So anyways, that gives you an idea. It's just a variable resistor. So how cool is that? So what I'm going to do, just to kind of show you how things are in the lab sometimes. So the way we have it now is this is my positive rail right here. You can see that. And then here's my negative rail, and I've got a little wire here just where I can measure things. And I've got, this is the thermistor I was showing you right there. But we're going to set it aside for now and just kind of measure. So this should be, this guy right here, I'm just going to measure this resistor. Oh, I'll measure it this way. This resistor should be, okay, that's 4.7-ish k ohms. So we're going to kind of put it on here. And, don't want to put it on that one. Okay, so what we have here is this is going from the positive rail down to the negative rail. It's maybe kind of hard to see, but you can see the blue one here. That's the negative rail. And then this one is, see, this one's 10K. So, and this one, so we're going to put it right here on the negative rail. And of course, I had measured this guy. Let me unplug this guy so I'll be able to measure it right. But see if I can get a good. So that's 4, and then this one is. Make sure it's 10 k ohms. Or I mean 4 k ohms as well. Yep, 4 k ohms. 4.7. I mean. All right. So what this circuit right here represents is. Okay, so what this circuit represents, let me unplug this guy. Okay, so now we have in essentially made this circuit right here, the one that we just drew, the first one that we drew for the lab. It's 4.7K across the top, and then we got 10K down here, and we're going to measure right here. And I'm really in a perfect world this would be 0 volts, but what I'm trying to demonstrate here is. This is not a perfect world, right? So what I'm going to do is measure. What I'm going to do is put. Now this is I need to change this to volts because this is going to be a voltmeter. So now I've got it set to volts, and so what I'm going to be doing now is measuring. This is point A and this is point B. So I'm going to be measuring the voltage. So when I turn it on, now I've got 0.84 volts, and the reason I have that is, it's close to 0, but these values are off a little bit. Like this one, is not perfectly 4.7. This one isn't even, and this one isn't perfectly 10.k ohms. So that's why if they're static and not changing, and unless they had 0% tolerance, which I don't know of any resistor that does, you're going to have, it's going to be off a little bit. It's not bad though, but it's still off. It's not perfectly zero. So let's go in and add the potentiometer, and so let's power this guy off, and we're gonna pop in a potentiometer now. And the way we'll do that is we'll take our potentiometer, and I know it's kind of hard to see probably, but I'm gonna try to see if I can get it in here as close as I can. Actually, I might just put it right here, and there we go. And then that's what's so cool about these breadboards is you can move them around and stuff. So I'm gonna, oops, I dropped it. So I'm gonna take this, I'm gonna put it right here. So I'm gonna take this guy, and okay. So what I'm doing is I'm just trying to put that potentiometer, like, you know how, like right here, I'm just trying to put a potentiometer in there, is what I'm trying to do. And I should be able to, if I can get a wire over there. Let's see, so I'm going to grab a wire, and I'm going to have ground right here, and I'm going to see if I can run a wire into that guy. I wish you could see a little better in there, but you can, I don't know if you can see it. You can kind of see how I ran. There's a resistor running in here, and it goes to this end of the pot, and then right here, the center one, I'm tapping off the center one with this wire. So anyway, so now what I can do, I'll put my resistor over there. Let's power it up and see if we can measure what's going on between A and B. It's going to be kind of hard to measure because I don't have a good, and hopefully I won't pop anything loose. Okay, so now what I'm going to do, hopefully you have my meter. Now, so you can see it's off a little bit. I'm going to adjust that potentiometer. Now, see how it's changing? I'm only changing this potentiometer. And what's happening is now I'm going to start lowering. It's getting lower and lower. And see, now it's approaching the 10K ohms. So now, or it's matching this resistor is really what it's doing. And let's see if I can adjust it a little. Oop, there we go. Oops, it's off just a little bit. There it is. Perfect zero. Well, I was going to say perfect. There for a second it was perfect, but, But anyway, you get the meaning. There you go, 0 volt. We'll call that 0 volts. And so now it's perfectly balanced. So I just want to show you that in a real world, if you're using fixed resistors, it's probably going to be off, and that's why you need that potentiometer. Okay, so now what we'll do is we'll get it set up for the thermistor. Okay, so now we have the thermistor, and that's this little guy right here. And I'm just going to pull it to the side, kind of like this, just so I can, and it's really not doing anything. I just want to measure it and show you what it's doing. So we're going to plug up. This is my voltmeter I'm plugging into it. I mean, actually it's my ohm meter. Ooh, I got to be careful these don't short out. I don't want to short across the resistor. So okay, so it's all right. So that's all good. So this is my ohm meter now, because I'm measuring resistance. I don't want to be measuring voltage, because what I'm trying to do is just show you how the resistance is going to change. So I'm just sitting here by itself. So right now I'm measuring, like the other day it was like 12, right? But it's a little above 10K. So I had that 10K pot that is too small. I can't balance it. But now if I pinch it and start heating it up, see the voltage is dropping? So that's just the thermistor changing resistance based on temperature. And then when I let loose, it'll start cooling off again, and then the resistance will go back up. So that's the problem I have. I have a situation where I've got to put another resistor in here to match the resting, I was going to say resting resistance. The default resistance where it's like room temperature. But what I'm going to do is I'm going to wire up the thermistor first, kind of show you how to do that. And so I've got it here, and then I'm just going to put a little wire here and then run that into ground like that. So now, I've got current flowing through this resistor, through the thermistor to ground. I've got current flowing through this end of the potentiometer to that little wiper thing where I can change the resistance to here. But what I've got to do is I've got to add a little bit of resistance to this potentiometer so that I can match the resistance of this guy. And to do that, I'm going to see if I can find a resistor that's, I'm just using what's at hand. Now that's 10K. That's a little too much. One thing about, these, you don't want to use a lot of resistance. Like, you don't want to use I wouldn't want to use like a 100K ohm resistor because it's harder to balance the bridge because you got so much resistance in there. It's hard for it to balance right. So you want to pick something. I probably wouldn't go over 10K ohms because then it gets a little harder. So you got more chances for error. So there's 4.6K ohms, and I just need to. I mean, even if I had a 1K ohm, probably I'd be fine, or maybe a 2K ohm. But this is all I have available in the lab. So what I'm going to do is I'm just going to take this guy and plug him into ground, and then I'm going to take this guy and tap into it. Okay. And so ultimately what I have is, what I just did was, and I'll kind of put this to the side and sort of show you. So what I did was, I just took this so we're at ground here, right? We're on the negative side of the battery. I just took that resistor, that little 4.7K ohm resistor, I wired it in series with this variable resistor. So now that's like 14.7K ohm variable. Well, 10K of it's variable, but it's enough to match this guy. And then, so here's point A, right here, and then there's the 4.7K ohms going up to the positive rail, and then right here, this is the 4.7K ohm resistor R3. So that's R1. This is R2. All of this here is R2. This is R3, and then of course RX is our thermistor, and it's going to ground. So that's kind of what we have. And so now what I want to do, and always remember, and I struggle with this too, so don't worry if you accidentally do it, but I always sometimes it's easy to forget, like to what polarity you're on, or sometimes it's easy to forget to plug up something, so don't ever beat yourself up over that. So because sometimes you'll forget to hook up a meter or whatever, and see, I've got to change this to voltage now. So I've got it on the 20 volt reading, and I'm going to see if I can tap into. I don't want to touch that potentiometer just because I'm not sure. I don't think it would throw anything off, but okay. And we got this where we can. I want to kind of see, have it where you can see it. So let's power it up. See what we have now. Now it looks like we are. Yeah, let's see if I can move it this way. Now we are at 0.3 volts on this guy. So let's see if we can get it balanced first. Okay, there we go. So that's the first thing you want to do is balance the bridge. And it's kind of easier said than done. I mean, it doesn't have to be perfect, but I like to, have it. I'd love to have it at 0. I mean, we're so close that it really doesn't matter, but I'll spend, okay, good. Okay, so we got it at 0, well, ish, right? And that was just for me moving a little bit. So it goes to show you how sensitive this guy is. So that's 0. Now, if I touch the thermistor, notice how it's going up in these little small increments. Before it was going up and down in big increments, but this is voltage we're measuring. So it goes from 0 to like 4.3 volts. And if I let off, it'll go back down again. So essentially what we've done is we've built a sensor, right? And so I could put like a light sensor, a light sensitive resistance in here, where if you turn on the light, and it changed the light variable, this low voltage would vary. And what you'll see in real life is this small voltage can be used to like an Arduino or something, or a controller, to read these little changes in voltage and then tell how hot something is. So in this case, I'd have a thermometer, and what you could do is you could plot like whatever temperature it is. Let's say it's 70 degrees in the room. Well, 70 degrees would equal 0 volts, and then 71 degrees might equal 1 volt, as you heat up. And then, on up. So then 2 volts might be 72 degrees, and 3 volts, 73 degrees, whatever. And you could keep plotting that, and then you could actually build a little thermometer. But that's about as far as we'll go here, because that's all the stuff I have available to work with, and the video's running kind of long. But anyway, so that's basically, that's the basic function of Wheatstone Bridge, is just to know what this resistance is. And, like when it's 0, like we could literally measure that. Of course, if I picked it up, it'll change it, but I could literally measure this, and I could measure all these, and these 2 branches at 0 volts would be the same ratio. So really neat, and very useful even today. So thanks for taking the time with me on the Wheatstone Bridge, and I'll talk to you next time. All right, well, thanks everyone for taking the time to spend with me on the Wheatstone Bridge. But before you go, I'd like to leave you with an encouraging verse from the Holy Bible. It's John 3:16. For God so loved the world that he gave his only begotten Son, that whosoever believeth in him should not perish, but have everlasting life. All right, well, thank you, and take care.